The modulus function. In the simplest terms possible, you can think of the modulus function as a tool that tells us how far a number is from zero on a number line. Welcome, everyone. Today we are going to begin a new topic, the modulus function. Before we dive into the formal mathematical definitions and complex notation, I want us to start with the core intuition behind this concept. It doesn't care about the direction, whether you are moving left or right. It only cares about the absolute distance from the starting point of zero. Keep this idea of distance in mind as we will use it to unpack the formal definition in our next slide. Formal definition. Now that we have a basic intuitive idea that the modulus function measures distance from zero, let's look at its formal mathematical definition. We represent the modulus function as f of x, where the function maps from the set of all real numbers to the set of all real numbers, and we use the notation f of x equals the absolute value of x. Now you might notice something interesting here. Unlike a simple linear equation, the rule for calculating our output actually changes depending on what number we plug in. Because of this, we express the modulus function as a piecewise function. If you look at the bracket here, you'll see the two different rules. In the first case, where x is greater than or equal to 0, the function is simply x. This means if the input is positive, the output stays exactly the same. However, in the second case, where x is less than 0, the function is defined as negative x. Don't let that negative sign confuse you. As we will break down in the next slide, this is actually the mathematical trick we use to ensure our final result always turns positive. Breaking down the definition. Now that we have seen the formal piecewise definition on the previous slide, let's break down exactly what those two different rules are actually doing to our input. First, let's look at case 1, where x is greater than or equal to 0. In this scenario, if you plug in 0 or any positive number, the function essentially leaves it alone. It does nothing to the value. The output is simply the number itself. So, if you start with a positive 5, you end with a positive 5. Next, we have case 2, which applies when x is less than 0. This is the part that often confuses students. When the input is a negative number, the rule tells us to use negative x now. Don't let that minus sign trick you into thinking the answer will be negative. This notation actually means we are multiplying the input by -1. Since we know from our basic arithmetic that a negative times a negative results in a positive, this step effectively flips the sign, ensuring our final result is always positive. This brings us perfectly into our next slide, where we'll use this logic to visualize this concept as the physical distance from 0. Real-world intuition, the concept of distance. Now that we have looked at the formal, piecewise definition of the function, I want to step away from the algebra for a moment and give you some real-world intuition. A very helpful way to understand the modulus function is to think of it simply as distance. In the physical world, we know that distance can never be a negative value. You can't walk a negative amount of kilometers, right? Let's look at an example to make this concrete. Imagine you are standing at point 0 on a long, straight road. Suppose you decide to walk 5 kilometers to the right, which we represent as the positive direction. When you stop, your distance from your starting point is exactly 5 kilometers. Now imagine instead that you walk 5 kilometers to the left, which is the negative direction. Even though you moved in the opposite direction, if you check your pedometer, your distance from the start is still exactly 5 kilometers. The direction changed, but the magnitude of the distance remained the same. Mathematically, we represent this exact concept using the modulus notation. We can say the modulus of 5 equals 5, and the modulus of -5 also equals 5. This perfectly illustrates why the output of our function is always non-negative, a concept we will use to evaluate specific numbers in the next slide. Step-by-step evaluation. Now that we understand the formal definition and the logic behind the piecewise rules, let's put that theory into practice. To find the value of the modulus function for any real number, you don't need to guess. You simply follow a consistent, step-by-step process. Let's look at example A, where we want to evaluate f of 7. First, identify your input, which is x equals 7. Next, we check our conditions from the definition we saw earlier. Is 7 greater than or equal to 0, or is 7 less than 0? Since 7 is a positive number, we know it falls into the first case, where x is greater than or equal to 0. Because of this, we apply the corresponding rule, which tells us that f of x equals x. So our final result is f of 7, which is the modulus of 7 equals 7. Now, let's try something slightly more complex with example B, evaluating f of -12. Step 1, identify the input, which is x equals -12. Step 2, check the condition. Is -12 greater than or equal to 0, or is it less than 0? Since -12 is a negative number, it falls into our second case, where x is less than 0. Step 3, apply the rule for this case. As we discussed in the previous slides, for negative inputs, the rule is f of x equals -x. Step 4, perform the calculation. We take the modulus of -12, which becomes negative of -12. As you know, a negative times a negative gives us a positive, so this simplifies to 12. Therefore, our final result is f of -12 equals 12. As you can see, the process is always about checking which branch of the function your number belongs to before you do any math. Now, let's visualize what this looks like on a coordinate plane. Graphical representation. Now that we have mastered how to evaluate the function numerically, let's visualize what this looks like on a coordinate plane. The graph of the modulus function, f of x equals the absolute value of x, is very distinct and quite easy to recognize once you see it. To understand how to draw it, let's look at the two parts of the piecewise definition we discussed earlier. First, let's look at the right side, where x is greater than or equal to 0. In this region, the function follows the line y equals x. This is a straight diagonal line that starts at the origin, which is the point 0, 0, and moves upwards to the right. Next, let's look at the left side, where x is less than 0. Here, the function follows the line y equals -x. This is also a straight diagonal line starting from the origin, but instead of going right, it moves upwards to the left. The point where these two lines meet at the origin, 0, 0, is called the vertex. When you put these two pieces together, the resulting shape is a perfect V-shape that is symmetric about the y-axis. And, as we learned in our previous examples, where we saw that the output is always positive, you'll notice that the entire graph lies on or above the x-axis. This leads us directly into our final summary of the key properties of this function. Key takeaways. First, let's look at the domain. As we saw in our earlier examples, you can plug any number, whether it is positive, negative, or 0, into the modulus function. Therefore, the domain is the set of all real numbers, which we denote as R. Next, we have the range. If you look back at the graph we discussed in the previous slide, you'll notice that the V-shape never dips below the x-axis. The outputs are always 0 or positive. So, we define the range as the set of all non-negative real numbers, which can be written in interval notation as the bracket 0 to infinity. This leads us directly to the core property of the modulus function. The output is always non-negative. Mathematically, we express this as the absolute value of x is greater than or equal to 0 for all x in the set of real numbers. This is the fundamental rule that prevents the function from ever producing a negative result. Finally, let's consider the geometry. To summarize the visual aspect, the graph is a V-shaped curve with its vertex, or the sharp turning point, located exactly at the origin, which is the point 0, 0. Now that we have explored how to evaluate the function and how to visualize its graph, let's wrap up this lesson by summarizing the key takeaways you need to remember for your exams. Keep these properties in mind, because in our next slide, we will discuss some common pitfalls where students often trip up when applying these very rules. Common mistakes. Now, before we wrap up our lesson, I want to address two very common pitfalls that students often encounter when first learning about the modulus function. Being aware of these now will save you a lot of frustration in future exams. First, let's look at mistake number 1. The misconception that the expression negative x implies the final answer will be a negative number. When you look back at our formal definition on slide 2, you saw that for any input where x is less than 0, the rule is f of x equals negative x. It is very easy to see that minus sign and instinctively assume the output will be negative. However, please remember the correction we discussed during our step-by-step evaluation. The variable x itself is already a negative value. Therefore, applying a negative sign to it actually means you are taking the opposite of a negative, which results in a positive. For instance, if we take x equals negative 5, then negative x becomes negative 5, which simplifies to positive 5. Always keep that distinction in mind. Moving on to mistake number 2, confusing the modulus function with a standard linear function. It is quite common to see students treat the absolute value of x as if it were simply the straight line, y equals x, while the right side of our v-shaped graph does indeed follow the line y equals x. A standard linear function would continue straight down into the third quadrant, where both x and y are negative. But as we saw in our graphical representation on slide 6, the modulus function behaves differently. It effectively reflects that negative portion of the line across the x-axis. This reflection is what ensures the output is never negative, creating that characteristic v-shape we've studied today. By keeping these 2 points in mind, you'll have a much stronger grasp of how the modulus function operates.